now we come to two different versions of conversion methods. Question is why we need more. I don't want to hide disadvantages. Disadvantage. There is no general solution for any f of p. You need a table. Of course, you can find many tables. See internet, yeah, many tables. If you Google this, no problem. You can find big tables and so on. But then the conversion must be done manually. I have no mathematical tool who can do this automatically. Conversion must be done manually. Okay, so in my tool program I have prepared for special filter functions. I've prepared this step response invariant filter form. Let's have a quick look on my program. Yeah, if you open the hardware simulator, you can see that I have done this for PT1, IT1, so an integrator with one delay, two PT1s, PT2 with damping smaller one or larger one, independent, for a connection of 3 PT1 or 4 PT1. So these are six types which are prepared, but not more. Of course, you can use my hardware simulator with any f of z. If you have found an f of z, put your variables here and then be happy. But just, you see, I have manually done 6 filter function conversions, not more. If you have a different one than this, then you have to go into a table and do this manually. So it would be nice to have a method which can be done simply with a tool, with a calculator, to throw out the result for any FFC. And the next steps I want to show are exactly useful for this. So let's continue with the third method of conversion. This is, I call this rectangular approach. Rectangular approach. Why this is called rectangular approach, we will see in the end of this sub-chapter. Okay, the idea is very simple. The replacement of the Z transformation is explained earlier in this chapter, is e to the power of complex frequency times sampling time. Of course, you can turn it around and solve this equation to p. If you do this, you get p is 1 divided by sampling time, and the inverse exponential function is the logarithmic function of z. So this is the exact replacement, inverted replacement of the complex frequency p. And for example, if you put this p into your analog filter transfer function, for example our PT1, what happens? That you get an f of z. F of z is k divided by 1 plus, and now p comes is time constant divided by sampling time multiplied with logarithmic function of z. Okay, so we can say the mathematical scientist is happy and say, okay, this is the exact digital filter. The engineer says, okay, how can I realize it? I can't. Yeah, this is not realizable because it's not normalized form. So no algorithm available. You cannot program it. So we need one step more, and the trick is now the logarithmic function cannot be programmed, but I can find an approximation for the logarithmic function. Now use approximation via Taylor series. Taylor polynomial function gives a good approximation around one point exact, and around this point approaching the correct value. So around, now the question is, where is the a good development point of a Taylor series? Working point, equilibrium point, or what you want to say for this. In the digital filter theory, we select the DC point around Z is 1. That is the DC case. So we get an approximation which is exact for Z is 1, and around Z, so for low frequencies, maybe we have a good approximation. Let's see. If there are two different forms of Taylor series, if you look into mathematical books, you can find the following approximation, and 7.23 is one, and 7.24 is a better one. So we start with a simple one, and the simple replacement is P roundabout, 1 over t sampling time is of course unchanged, and the logarithmic function then can be replaced with 1 minus z to the power of minus 1. This is exact in this case. If z is 1, you see z is 1, then 1 minus 1 is 0, and p is 0. That is a DC case. So in DC case, exact. For low frequencies, also a good approximation. And this replacement is called rectangular approach. Let's do the example. This can be done manually, but I will show you after my manual work. My tool program WinDFC can do this for any filter function automatically. This can be programmed. I can find a method, a procedure, which can replace in any FFP the P with this, and then you get the coefficients of a digital filter. You can program it. That's a very nice feature of this method. Let's do this with our f of p. So we get an f of z, which is k divided, look here, k divided by 1 plus, and now p replaced with this gives t divided by sampling time multiplied with 1 minus z to the power of minus 1. This is not the normalized form. I just separate the coefficients. There is this t divided by t sub o times 1. So this is the 1 plus t divided by t sub o, the element without a z, function, minus t divided by sampling time times c to the power of minus 1. So now normalize. Note that the normalized form norm of f of z, which can be easily converted into an algorithm, is written as q0 plus q1 z to the power of minus 1 plus and so on plus qn z to the power of minus m, and the normalized form here needs a 1 here, and then minus p1 z to the power of minus 1 minus and so on minus pm z to the power of minus n. Okay, so this element here without a z has to be forced to a 1, so we have to divide by 1 plus t divided by t sub o. So the normalized f of z finally ends in k divided by 1 plus t divided by t sub o. In the numerator, and in the denominator our normalized 1, and then minus t divided by t sub o divided by 1 plus t divided by t sub o times z to the power of minus 1. Then you see this here is q0 and this is p1, and we can at once write the algorithm in our yx form. Y of n is p1 y of n minus 1 plus q0 times x of n. With our values, q0 can be calculated in k is 2, number example, plus 1 plus t is 0.5 divided by 0.1. So this is 5 plus 1 is 6, 2 divided by 6 is 1 divided by 3. This is 0.33 period repeated, yeah. And q1 is 0, and p1 is positive. T divided by the sampling time is this 5 divided by 1 plus 5. This is 5 over 6, and this gives 0.833 repeated. And all other p's p2 to n are 0. So my algorithm finally sounds in yn is 0.833 repeated old value of output plus 0.33 period times x of n. Okay, that is the third PT1 filter. Let's compare again the step responses. Step response. Okay, yeah, I think see paper I have done this. The best is we look on the curves. I have done this, you know how to do this, yeah. We make an exercise, n is 0, 1, 2 and so on. X is 1, x of n, and y of n is, let's do the first step. The first element is, now y of 0 is any time the q is the highest with the lowest number, so this is 0.33 repeated, and so on. And the final value is interesting. We need the DC gain of our filter, yeah. Compare step response, see paper. I think this is paper page, let's just look, that is on page 29, paper page 29. And the DC value, DC gain, is f of z is 1. This q0 is 0.33 period divided by 1 minus 0.833 period, or 1/3 divided by 1 minus 5 divided by 6. And you see this is exactly 1 minus 5, 6 is 1 over 6, 1 over 3 divided by 1 over 6 leads in exactly 2. So the DC gain of my rectangular approach filter is exactly like the DC gain of my DC gain K was don't forget K is 2. So the DC gain fits accurately. We expect this because the Taylor series was developed around the DC point. So this must be exact at that point, and around this point, maybe a good approximation. See the curve in the paper. I just shift this paper into our video form, so you see here. See the table. That was the table, and that was the curve. The black curve is always the analog PT1 step response, and here you see the blue curve is now my rectangular approach filter. And see what happens here in the beginning. I can say the average of the blue curve is a little bit too high, and here in the ending you can say the average of the curve is a little bit too low, so too small. I think this is much better than my step response invariant filter, but it could be possible that this could also be improved. Wait for the fourth method. But I want to stay here and want to show you how to do this now with a computer algorithm first, and second I want to show why the name of this filter method is rectangular approach. Let's have a look back into chapter 6.2.2 of the paper. There I have developed an algorithm for a pure integrator. The pure integrator has a gain K sub I, and the integration is shown here with the integral relation. And remember, I have then replaced the integration, the area under this curve, by a sum of rectangles. My green version including the last rectangle. The result then of the algorithm, the recursive form in green was this, and we can say, okay, yn is the output. You see the output needs the exact old output with a gain 1, with a coefficient 1. So we can say, okay, the P1 coefficient of my integrator is 1, and then it's added the input value, actual input value, same index here, with Ki times sampling time. This is the Q0 factor. So we can say, copy now this into my paper to compare what we get with our rectangular approach with Z transformation support. Comparison of I algorithm of chapter 6.22. There we have yn was yn minus 1 plus x of n times ki sampling time. The P1 is 1 and this is Q0. Now we do this with our rectangular approach. Now with 7.2.3 P replaced with 1 over sampling time times 1 minus z to the power of minus 1. Put this into f of p is ki divided by p. That is the integration transfer function. We get an f of z, which is ki divided by my replacement, is 1 over sampling time 1 minus z to the power of minus 1. This gives ki times sampling time divided by 1 minus e to the power of minus 1. This is note, this is the Q0, and this is P1 equals 1. That is exactly same result, and that is true for all other designs we have done in chapter 6. So we can do this in this chapter 6 way by replacing differential equation into difference equation. That was the name for this method. But now we get exactly the same result as if we replace our P with my replacement 1 over T sub O times quantity 1 minus e to the power of minus 1. So that is the reason for rectangular approach, because I replace in chapter 6.2 I replace the integration with the sum of rectangles, rectangular approach. Okay, so far I want to show you how to get this method. No, I think I show this application after I finish the theory of the fourth method. Yeah? Why a fourth method? 7.2.4 because it goes better than 7.2.3. This is the trapezoidal approach or approximation. In mathematical books there are two different Taylor series expansions. This is the simplest one, but a next step of accuracy gives the following form. Taylor version 2 delivers P replaced with 2 divided by sampling time. The numerator is the same, negative sign, numerator is the same, 1 minus e to the power of minus 1, and the denominator carries now 1 plus z to the power of minus 1. This is in literature called, there are different names, called bilinear transformation. You can find, if you Google this, yeah, bilinear transformation. Just coming from the fact that you have a linear function in the numerator and a linear function in the denominator. Or there was a very old literature publication from the two scientists Boxer and Thaler, and they do the same, have done the same, I think 40 years ago or so. So some people know this replacement as Boxer-Thaler transformation. It's all the same. Why I call this trapezoidal approximation? Very simple. Behind this method like in the previous chapter, I replaced the integration with the sum of rectangles. Behind this method, the integration is replaced by a sum of trapezoidals. This looks very similar to the following picture. I very quickly can sketch this. Note, if I have this curve, I have sampling points here and here and here. Now that is sampling time, 2 sampling times, and so on. Then the replacement not use the sum of rectangles, but the sum of trapezoidals. and you see the green area of the trapezoidals. What is a trapezoidal? Is much better. Note, in the rectangular approach, this triangle is missing. So you get a better approximation of the integrator. But you see there is some more work, or finally there are more coefficients, and you have to multiply. You have to need more multiplication, so the computer has to do more work. Example. Black. Let's do the job with our low pass filter. 2 divided by 1 plus p times 0.5. If you replace p now with our new function, then we get 2 divided by 1 plus 2 divided by sampling time multiplied with 0.5, and then followed the 1 minus c to the power of minus 1 divided by 1 plus c to the power of minus 1. We need here the normalized form. So we factor out this. We factor numerator and denominator with 1 plus c to the power of minus 1 and get here 2 times 1 plus c to the power of minus 1. Here the 1 in this expression has to be multiplied with this denominator, so we have 1 plus z to the power of minus 1 at this position, and here we have 2 times 0.5 is 1 divided by sampling time. This is a 10 in our case. 10 multiplied with 1 minus c to the power of minus 1. So in total, if I put all things together, we have in the numerator copy, in the denominator now I sort by these, so we get 1 plus 10 times 1 is 11 plus 1 minus 10, this is minus 9. Minus 9 times z to the power of minus 1. So we have to normalize. This 11 must be a 1, so we have to divide by 11. Okay, so we have here 2 divided by 11, 1 plus z to the power of minus 1, and here 1 minus 9 divided by 11, z to the power of minus 1. So in total we can say the Q0 is 2 divided by 11. Q0 is 2 divided by 11 with calculator and decimal numbers is 0.81 repeated. Q1 is the same, is 2 divided by 11 is the same, 0.81 repeated, and the Fehler, that's live. 2 divided by 11 is of course not, that is 0.18 repeated, 18 repeated, and P1 is 9 divided by 11, this gives this 0.81 repeated. This algorithm, we compare again the step responses of this filter with the analog filter, see resulting step responses. Page 30 in my paper. I shift this in my region, display region, and here you see the resulting curve. Look that again the blue curve here is the analog step response, and now the black curve is the resulting trapezoidal filter form step response. And if you see, now you can see, I think, that the average of the black curve fits absolutely good to the blue curve. So we can say that this is much better than the rectangular approach. So more calculation work, but better result. So most of all, digital filters then can be designed with a good effect as a trapezoidal approach. We have finally to compare the DC value. What is with the DC value? Z is 1. If we replace here Z with 1, then we see that in the numerator we have 2 divided by 11, so multiplied with 1 plus 1 divided by 1 minus 9 over 11 times 1, so this gives exactly 2, so it fits. In the next video I will show you, this is video number 19. In the next video I present the tool in the C# where I can do these steps automatically with a program, and finally I can compare the Bode plots, which is not possible in manually design.